Okay, so welcome to this next video in which we are discussing Pavlovian/classical conditioning. Okay, right. So we are in the process of discussing sensitization within the gill withdrawal reflex within Aplysia californica. Okay, so we've discussed that if you drop a water molecule onto the siphon of Aplysia californica, what occurs is the gill of Aplysia californica contracts over the siphon to protect it. This is called the gill withdrawal reflex. We've discussed that you can sensitize this gill withdrawal reflex by delivering an electric shock to the head of the Aplysia californica, which then means that if you drop water on the siphon again, the amount of contraction that you will get will be increased. So you deliver the exact same stimulus, but the response you're getting following the electric shock to the head is going to be hugely increased. We've then discussed that the neural correlate of this is that upon electrically shocking the head of the Aplysia californica, an L29 interneuron within the abdominal ganglion of the Aplysia californica becomes activated and has an axoaxonic synapse onto the L1 sensory neuron's axon terminal. This axon terminal of the L29 interneuron will release serotonin onto the L1 sensory neuron's axon terminal, and this will produce a change that lasts for a certain amount of time, okay, for a decent amount of time, for a significant amount of time. And this change is that every time the L1 sensory neuron now fires an action potential, the amount of neurotransmitter that will be released from the L1 sensory neuron axon terminal will be increased. Okay, so this means that even though you stimulate the siphon by the same amount, and that results in the same amount of activity in the L1 sensory neuron, each time the L1 sensory neuron fires an action potential, the amount of neurotransmitter that will result in being released from the L1 sensory neuron's axon terminal will be increased, which means that the amount of stimulation you are delivering to the L7 motor neurons, the L7 motor neuron, is going to be increased. So it's going to fire a greater number of action potentials, which means that the contraction you're going to get in the gill muscle will also be increased. We now want to discuss the actual molecular basis of L29 increasing the amount of neurotransmitter released by this axon terminal of the L1 sensory neuron. Okay, right. So, and firstly want to make sure everyone is on the same page with regards to action potentials, because really understanding the action potential is absolutely crucial to understanding how we are going to increase the amount of neurotransmitter that will be released by that L1 sensory neuron's axon terminal. Okay, so let's discuss the action potential, but we'll start by discussing the electrical potential difference across a cell membrane. Okay, so basically, electrical potential is this concept from theoretical physics. Okay, it is a mathematical model to help us understand reality. Okay, and this is the model. Basically, what you do is you go to every point in three-dimensional space and you ascribe it a real number. Okay, it can be positive, it can be 0, it can be negative. It can be integer, it can be rational, it can be irrational. It can be any real number. Okay, so you ascribe to every point in three-dimensional space a real number, and this is what's known as the electrical potential. So in principle, you can have a little man with a clever little machine, and he can go and stand anywhere in three-dimensional space, and he can measure what the electrical potential of that point is. Okay, now the units of electrical potential are volts. Okay, so everywhere is ascribed an electrical potential which will be measured in volts. Now, basically, all of the points of the intracellular cytoplasm will be in electrical equilibrium with one another and will all have the same electrical potential. So all of the points within the cytoplasm of the cell will have the same electrical potential. Okay, so this little man with his clever machine could go and stand anywhere within the cytoplasm of the cell and measure the electrical potential there, and he would get the same value. Okay, and we will call this value the electrical potential, big E for electrical potential, and then subscript it with an I to show that this is the intracellular electrical potential. Okay, so let me stress again, they're all in electrical equilibrium with one another, so all of them have the same value. Wherever you stand inside the cell, the electrical potential will be the same, basically. Okay, providing you're in the cytoplasm. Okay, so that's what's meant by the electrical potential intracellularly. Okay, then you can go into the extracellular fluid. Okay, and all the points of the extracellular fluid are in electrical equilibrium with one another, and therefore they will all have the same electrical potential, which we will call big E for electrical potential, and then we'll subscript it E as well for extracellular. Okay, now these two numbers are not necessarily the same. Okay, so the electrical potential extracellularly is not necessarily the same as the electrical potential intracellularly. Ergo, there is an electrical potential difference across the cell membrane. Okay, so electrical potential difference is also called voltage. Okay, now strictly speaking, when people talk about the electrical potential difference across the cell membrane, what they really should say is the electrical potential difference, or the voltage, from extracellular to intracellular. They should tell you what direction they mean. Okay, people generally forget to tell you this. They drop it. Okay, they assume that you understand that they mean from extracellular to intracellular. Okay, so what does this actually mean? Well, basically this means if you had a little man standing in the extracellular fluid and he measured the electrical potential there. Okay, so let's say our little man starts off in the extracellular fluid and he measures the electrical potential there and he gets this value. Then, if he moves from the extracellular fluid into the intracellular fluid and measures electrical potential again, he'll get a different number. He'll now get this number. Okay, the electrical potential difference from extracellular to intracellular means how much will this number change when he moves from extracellular to intracellular. So how much does the number on his screen change when he makes this jump from the extracellular compartment into the intracellular compartment? Now, what's the answer to that? Okay, well, basically, it's going to be the new electrical potential on his screen, so the electrical potential intracellularly, the one after the transformation has occurred, subtract the old electrical potential on his screen, which is the electrical potential extracellularly. So the electrical potential difference across the cell membrane, which strictly speaking we should call the electrical potential difference from extracellular to intracellular, is the electrical potential of the intracellular compartment subtract the electrical potential of the extracellular compartment. Okay, now usually this is around negative 65 millivolts. Okay, now what that means is that if the little man moved from the extracellular to the intracellular compartment, the number on his screen would go down, that's the negative, and it would go down by 65 millivolts. So the electrical potential intracellularly is lower than the electrical potential extracellularly, and it's lower by 65 millivolts. Okay, so that's what electrical potential difference means. Now let's talk about the concept of an action potential, because an action potential is a rather fancy orchestration of changes in the electrical potential difference across the cell membrane. Okay, so what it will begin with is some sort of initial depolarization of the cell membrane. Okay, so if we think about the L1 sensory neuron, okay, so here is the L1 sensory neuron here, and then basically when I squirt water onto the L1 sensory neuron, something has to change in the terminal of this L1 sensory neuron that actually triggers an action potential in response to the water. So the water has to produce some response. Now generally what happens is that you open a sodium channel. Okay, so generally the way that a sensory stimulus, such as the water, okay, so I'll call this sensory stimulus, the general way that a sensory stimulus promotes an action potential in the sensory neuron is by resulting in the opening of sodium channels. Okay, so here is my sodium channel here. So this is my sodium channel, which I am sort of just going to state is coupled to the sensory stimulus. I don't actually know whether it is the sodium channel that detects water specifically, but for conceptual basis, we can imagine that it's going to open the sodium channel. Generally it is. Okay, so we'll call this a stimulus-coupled sodium channel. So that just means that the stimulus somehow is going to lead to this sodium channel opening. So this is a stimulus-coupled sodium channel. Okay, now, there's one little bit more information that we need, which is the normal concentrations of sodium extracellularly and intracellularly, and the normal concentrations of potassium extracellularly and intracellularly. So the normal concentration of sodium extracellularly is around 145 millimolar, whereas the concentration of potassium generally extracellularly is around 4 millimolar. The concentration of sodium intracellularly is usually around 12 millimolar, and the concentration of potassium intracellularly is usually around 155 millimolar. So basically, there is a concentration gradient of around 12-fold of sodium across the cell membrane. So the concentration of sodium extracellularly is around 12 times bigger than the concentration of sodium intracellularly. There is then around 40-fold gradient of potassium across the membrane, and the potassium concentration intracellularly is around 40 times bigger than the potassium concentration extracellularly. Okay, so basically, this is how action potentials generally are initiated. The sensory stimulus will come in, okay? In this case, it's the water being squirted onto the siphon. This will cause the opening of this sensory stimulus coupled sodium channel in the membrane of the sensory neuron. Okay, so this will open, and of course there won't just be one of them, you'll have multiple of them in this area, and they'll all be opening. Okay, and when they open, that will allow sodium ions to move through them, okay? And we have to think which direction are sodium ions going to move in. Now, I've kind of given it away, but let's think this through. Which direction are sodium ions going to move in? Well, basically, we've got a 12-fold gradient of concentration of sodium, which is favouring the movement of sodium in, simply because a sodium ion on this side is 12 times more likely to hit the channel from this side and go through this way than a sodium ion on this side is to hit the channel from this side and go through that way. So this is favouring the movement of sodium in. In addition, we have to consider the electrical potential difference across the cell membrane. Now, we are working on the basis that the electrical potential difference at rest is around negative 65 millivolts, which means that the intracellular compartment's electrical potential is lower than the electrical potential of the extracellular compartment, and it's lower by a whole 65 millivolts. Okay, sodium ions are a positively charged ion. Okay, they will prefer to be in the compartment with the lower electrical potential, which in this case is the intracellular compartment. Okay, so they want to be in the intracellular compartment. So both the concentration gradient and the electrical gradient are favouring the movement of sodium in. So when you open this stimulus-coupled sodium channel, that will then cause the entrance of sodium into the cell, basically. Sodium will move into the cell. Now, what's the effect on the electrical potential difference of moving this sodium into the cell? Okay, well, sodium carries a positive charge, so you are moving positively charged particles out of the extracellular compartment and into the intracellular compartment. Where there is positive charge, you increase the electrical potential. So basically, by dumping a positive charge into the intracellular compartment, we are going to raise the electrical potential of the intracellular compartment. So the intracellular electrical potential is going to go up because of the movement of sodium in. Meanwhile, we are removing positive charge from the extracellular compartment, which means that the electrical compartment's electrical potential, sorry, the extracellular compartment's electrical potential is going to go down. So this number is going to go down because we're losing positive charge, and positive charge increases the electrical potential. So if you move positive charge out, you're going to lose electrical potential. So the electrical potential of the extracellular compartment is going to go down. Okay, what effect is this then going to have on the electrical potential difference across the cell membrane? So remember, initially the electrical potential difference was negative 65 millivolts, which meant that the intracellular electrical potential is 65 millivolts lower than the electrical potential extracellularly. Okay, now we are moving the electrical potential extracellularly down, and we're moving the electrical potential intracellularly up. So the amount that you're going to have to go down in electrical potential if you move from the extracellular to the intracellular compartment is going to get less. So this number is going to become less negative, basically. If you want to see that just from the equation, this number here is going up. This number here is going down. Okay, so this number, which is got a plus in front of it, effectively, is going up. The number that you're subtracting off is going down, so that overall the answer you're going to get is going to become less negative. So you're going to cause a depolarization of the electrical potential difference across the cell membrane. So the conventional thing to now do is to plot a graph, okay, and it is actually quite helpful. Okay, so let me just raise that axis a bit. So on the y-axis, we are going to plot the electrical potential difference from extracellular to intracellular. Okay? On the x-axis, we are going to plot time. Now, initially, the electrical potential difference across our cell membrane was fixed at negative 65 millivolts down here. Okay? Then we delivered the sensory stimulus. Let's say we delivered the stimulus here. It caused the opening of these sensory stimulus-coupled sodium channels, and that is now causing the depolarization of the electrical potential difference across the cell membrane. Now, if the depolarization that the opening of these stimulus-coupled sodium channels produces is great enough to take you up to negative 40 millivolts, okay, then what will happen is you will open another type of channel in the cell membrane. Okay, so this is called threshold potential. Negative 40 millivolts is called the threshold potential for the firing of the action potential. And the reason it's the threshold potential is because this is the electrical potential difference across the cell membrane that you need in order to activate the opening of the voltage-gated sodium channels. So let me draw these here. So basically, in the cell membrane, you have a special type of channel called a voltage-gated, and then I'll put N for sodium, C, VGNC, voltage for V, G for gated, N for the periodic table symbol for sodium, and then C for channel. Okay, so let's cover these voltage-gated sodium channels in yellow, in green here. Okay, so basically, these are going to be activated to open when the electrical potential difference across the cell membrane goes up to negative 40 millivolts. Okay, so these have now opened, providing we got to negative 40 millivolts. Now, what's the result of this? Well, basically, they are going to do the same thing that the stimulus-coupled sodium channel did, but they're going to do it far, far better, basically. Okay, and not just one of these is going to open. You're going to have loads of them, and they're all going to open. Okay, and this is occurring at a little portion of the cell's membrane. Okay, so we've got a little portion of the cell's membrane here that is undergoing this change. Okay, so these voltage-gated sodium channels open. They allow sodium to enter the cell. That causes further depolarization of the electrical potential difference across the cell membrane. So you get a really rapid depolarization of the electrical potential difference across the cell membrane. And this is known as the upstroke of the action potential. And generally it gets to around plus 40 millivolts. So it gets to the point where the electrical potential intracellularly is actually greater than the electrical potential extracellularly, and it's greater by 40 millivolts. Okay, right, so if you move from the extracellular to the intracellular compartment, your electrical potential will increase by 40 millivolts. Now, basically, the voltage-gated sodium channels, they open extremely rapidly when you get to threshold potential, but they also close very rapidly. So they stay open for an extremely short period of time. Okay, this little period here that I'll now highlight in pink, and then they close. So these voltage-gated sodium channels are going to start closing, basically. Okay, so what I want to stress is that it's not the fact that we've got the electrical potential difference across the cell membrane to plus 40 millivolts that causes them to close. That's a common misbelief. They close after a certain amount of time, and after that amount of time, it just so happens that the electrical potential difference they've got the cell membrane electrical potential difference to is plus 40 millivolts. Okay, right. Now what's going to happen is you're going to get the opening of the voltage-gated potassium channels, which I'll put over here. So, let me colour these in an orange. So, basically, voltage-gated potassium channels are going to open at this point here. Now, they were not activated to open by the fact that we've got the electrical potential difference across the cell membrane to plus 40 millivolts. They were actually activated to open all the way down here. They were activated to open at around the same threshold potential as open the voltage-gated sodium channels. So here in orange, this is a voltage-gated potassium channel. K is the periodic table symbol for potassium. Okay, the difference between them and the voltage-gated sodium channels is that the voltage-gated sodium channels open extremely rapidly, whereas the voltage-gated potassium channels take absolutely ages to open.